happy to be here. First, I would like to thank all the organizers of the conference. We're having a really good time. They've been doing a really good job. So I'm Radu. I work at the European Organization for Particle Physics Research, also called the Cern, and which is located outside of Geneva, Switzerland, and is the home of the Large Hadron Collider, which, as you know, is the particle accelerator that helped confirm the existence of the Higgs boson. So this accelerator is indicated here in the image by the yellow circle. And just to give you a sense of scale, you could almost fit the entire city of Geneva inside the circle. So Geneva is this, basically, here, with a bit of a few neighborhoods here on the other side. So you can see you can actually put them inside. So this accelerator is 27 kilometers long. And inside it looks like this tunnel, which is about 100 meters underground. And the power used is about 180 megawatts, which is actually equivalent to all the households in Geneva combined. So definitely we're raking up the biggest power bill there. And the energy developed by the accelerator is about 7 tera electron volts. So an analogy is, let's say this accelerates each particle to the energy of a mosquito buzzing around, but putting all the particles together in a coherent stream gives you the energy of a speeding train crashing forward. So at 4 different points along the length of the accelerator are the houses of 4 main experiments doing physics on the Large Hadron Collider. And these are independent entities, which they're looking at different questions, such as, why is it that we can only account for 5% of the mass in the universe? Or how did the Big Bang happen? And for instance, this experiment is called ALICE. This is CMS, if I'm not mistaken. This is ATLAS, and this is LHCb. These two are the largest experiments, and they're actually involved in more general physics research, and they were the ones that were able to confirm the existence of the Higgs boson. ALICE and LHCb are doing more specialized physics, and unfortunately I'm not a physicist, so I cannot go into more detail here, but you should look into it if you're interested. And at the center of each one of these detectors, you can find a silicon tracker. So this is a device like this big, and actually it's more or less equivalent in function to a digital camera sensor that you have in your smartphones. And this one is the inner barrel of the CMS experiment. So if you're familiar with this picture, or it seems familiar with you, it's maybe because you have this CD in your collection. So it's a good work. I can warmly recommend it. But now, as I said, so these are more or less digital camera sensors. They're about 100 million megapixels in resolution, but they have to be able to trigger once every 25 nanoseconds. So they're much more complicated and performant. And the data rate we are talking about is so high that you actually need specialized hardware around these things to be able to capture it and actually do a triage and a filtering there on the spot of the acquisition to bring it down to a manageable size that can be stored. So at this point, we are storing about 5 petabytes of data per year, which is including the various derived data sets. But in the next phases of the LHC experiments, which are expected to happen by 2025, we are looking at 100 petabytes of data per year, which is a 20-fold increase. Now, this is data. Then on the software stacks, which is actually the focus of my project, things are not so critical. We're just looking at 5 million lines of code per experiment. Now, also the computing infrastructure is quite particular at the CERN, since not everything is located at the Geneva site. You have a main data center there, but the CERN is also a collaboration of around 170 compute centers in 42 countries. which are pooling together their compute resources to be used for analysis and simulations. So this makes the worldwide LHC compute grid, which is running about 2 million jobs every day. And this is a plugin for Google Maps that is available. It shows the real-time usage of the grid. And when I took this screenshot, there were around 292,000 running jobs over 460,000 cores, which amounted to around 17 gigabytes of data transfer per second. So this is the computer architecture we're looking at. On the side of the LHC software stacks, we have hundreds of developers working on these projects, and at this point we have something like 100 million binaries that have to be stored and distributed. So we are producing around 1 terabyte new per day of software, so it has a high rate of change. And of course, it's the daily production releases that have to be stored and used on a longer term, while the nightly builds, they are pruned on a regular basis. Still, all this software has to make its way to the almost like 100,000 machines that make the worldwide compute grid. So it's a problem to think about and to solve. So this gives you a bit of context about the CernVM file system. So the origin of this file system is actually the so-called CernVM project. And this was an idea to create a reconfigurable VM appliance. So you had the CernVM that could be used in a certain configuration on a compute node, on the grid, or it could also be configured for interactive use by physicists on their laptops. But this project in its initial iteration was not very practical because of the large size of each one of these variations or each one of these configurations of VM, and then also to the time spent actually creating all these configurations. So for this, we created the CernVM File System, which meant that the base size of this appliance was 20 megabytes, with just the minimum amount of files and stuff needed to actually boot it and bootstrap it. And then all the contents even of the root partition are loaded through this file system. So this file system is actually a module for file system in user space. I don't know if you're familiar with this technology. You have various implementations such as SSH-FS and stuff like this. So it's a file system in user space that gives you a POSIX file system interface access to various remote repositories of software and files, which are either standard HTTP servers or S3 instances. And these repositories are made available through a global cache hierarchy, HTTP cache hierarchy for performance. So one thing that is very important to note is that the system is lazy. So when you mount one of these file systems, all that happens is that you have to download a bit of metadata to see basically the list of files currently available, but the content of the files will only be downloaded on demand when needed. So this makes things very, very efficient. Now, it's not a general purpose file system. It's a system where clients have a read-only view, while special designated writers have the only write access to the repository. So in a way, it's a publish-subscribe pattern. And HTTP is used as a transport exclusively, which simplifies the interaction of it with firewalls and many things. So the main components of this file system are the client fuse module, which is complemented by different cache plugins. So these are plugins that can actually improve the performance for specific use cases. So you can imagine that you're using it on a supercomputer where you have, for instance, many nodes that do not have local storage, but they are connected together by a very, very fast network. So there you can imagine some sort of peer-to-peer mesh plugin that could actually make performance much better for that case. So you have this flexibility. And you have a standard set of default plugins that come with the software. Then the server tools, which are supposed to run on this designated writer machine. These are command line tools. And for serving the files, we're using standard HTTP server. So it works with Apache or Nginx and all these things. HTTP cache is designed to use Squid. So we don't have to maintain these components, and we use industry standard, well-tested tools. So about the design of the file system, probably the most important design choice is the use of immutable content-addressed storage blobs. So all files are transformed into one or more of these content-addressed blobs. And things like the deduplication are coming for free, basically, from this implementation. We're also compressing all the blobs to store things more efficiently. And then for the metadata, we use SQLite catalogs to store all the metadata of the repository. So these are basically tables which are tying the content-addressed storage blocks to actual file names in the repositories and all the extra POSIX metadata, so file size, permission, and all these things. Here, you should note that we actually gave a lot of attention and a lot of effort to the POSIX compliance of the file system. So this system is supposed to run software. So on the grid, repositories are mounted, and all the software is run from the CernVM-FS mount points. So of course, in this use case, you're going to be hitting many more corner cases than if you're just storing data, so put get. So actually, a lot of effort went into making this as POSIX compliant as possible. Now, these metadata catalogs, you can see them basically as a Merkle tree encoding of the entire state of your repository at a given point in time. And of course, things like versioning and snapshots are also easy to implement and are available in this file system. And everything is PO-based, and this is important. So there will be no communication initiated from the server, from the centralized servers towards the client. Everything starts in the client requests a file, it gets a copy of it, it's cached, it has a time to live. And this means this system works as well, for instance, on a supercomputer or on a grid as on your laptop in hotel Wi-Fi, because you don't need a special configuration for the firewall to be able to access the repositories. Okay, so I mentioned that this is not a general purpose file system, but updating these repos follows a publish-subscribe pattern. So to publish, you have this this writer entity, let's say, implemented as a set of command line tools, and they're running on a special designated machine, which actually has direct write access to the storage of your repository. And this can be either a local mount or S3. And this writer is able to construct a read-write view of the repository with a union mount, such as overlay-FS or AUFS. And these tools are doing the job of compressing, hashing the files, and writing them to this repository storage. Then, after this step is done, new metadata catalogs are constructed and published. And finally, the repository manifest, which is a little text file that states the current revision number, the current root hash, all these things. This is swapped atomically at the end. And it's at this point only that the new state of a repository becomes available to all the clients. So this summarizes the existing workflow. You have a centralized release manager machine with which you interact directly. So you have to log into that machine and then run a few steps, and you have published to the repository. So this makes it quite straightforward to use. It's good for scripting, and it somewhat hides the fact that you're dealing with multiple machines with a distributed system. But as you saw, you're taking these locks, exclusive locks on the entire repository, so there's no support for concurrent writing into it with this scheme. And also, since you are basically expecting somebody to log into this machine, which actually has the repository storage mounted, this can be unsafe for certain installations. It depends on the client's installation. And then performance for the publication is enough for most cases, but we do already have some clients which have some more specific need to publish more files or larger payloads. And we're also looking at more use cases for this system. So we would also like to improve the performance a bit and be able to let's say, scale out to multiple release manager machines per repository. Some properties and constraints under which we are working. So considering the system as the repository and the cache and the clients, it's an eventually consistent system. Different clients can find themselves at the same time on different revisions. Once the publication stops, they will eventually converge to the same consistent view of the repository. And then, from the point of view of concurrency, there's a lot of concurrency to exploit here. So the immutability of the content-addressed storage blocks means that you never have a case where more than one entity actually is writing to these blocks. And also pushing these objects into the storage is idempotent. Then the directory tree structure of our data makes it easy to identify parallel branches where you should be able to operate almost completely independent. And of course, there is a critical section in the publication process which involves updating the metadata catalogs and swapping the manifest. But luckily, this part represents a small fraction of the publication process. So this is in our advantage if we want to parallelize this. So the starting point can be described as this. You have the user machine, and the user will connect to a machine serving as release manager over SSH. There you have the client and the server tools installed. You're making the publication, and this machine is able to access the authoritative storage of the repositories through NFS or S3. And this repository is then replicated and made available to clients. And where we went is here. So here you have multiple users, each accessing their own instance of the release manager machine. So here, basically, we improved the architecture by splitting the release manager machine into multiple machines with different roles. So in this new architecture, the release manager still does the so-called heavy lifting. So compressing, hashing the files, and then putting together payloads to send to the storage gateway. And this storage gateway is the new component. Its responsibility is receiving these payloads, unpacking them, of course, checking that everything is all right. It unpacks them, writes them to storage, and it also rebuilds the metadata catalogs as needed. Now the two parts are communicating through a well-defined service API. This is currently an HTTP API. And in this new architecture, as I said, multiple release managers can be writing to the repositories concurrently, but to maintain things consistent, the gateway has an extra responsibility, which is actually handing out exclusive leases to different release manager machines only to distinct subpaths of the repository. So the same directory is not modified at the same time by two release managers. And this, of course, simplifies things greatly. So we maintain the same workflow, but now we add an extra parameter to the CVM-FS server transaction command. We specify which subpath we want to acquire a lease for. So things are still familiar for the clients. So this new storage gateway component, as I said, it serves as a distributed lock manager for our system, checks the rights of different clients to modify the repositories, and is responsible for assigning exclusive leases to clients. And also, it does the work of receiving the so-called object packs, which are archives with multiple files and multiple content-addressed blobs. and writes them to authoritative storage. And for implementing this new component, so just as a parenthesis, everything up to this point is implemented in C++. So the client and the server tools are C++. But for this new component, we decided to go with Erlang and OTP to serve as distributed glue for this part of the system. And we went for this choice because we knew that the language and the framework have excellent support for concurrency and also for distributed applications. So we were attracted by the actor model of concurrency and also the different properties of the language, such as working with immutable values and functional constructs, the unique error handling approach of Erlang, and also the fact that you're dealing with let's say, battle-tested, proven technology. So you can benefit from all this all this experience. And of course, since most of our software is C++, you have good ways of interacting with C++ in Erlang, and this was important to us. So this basically describes the architecture of this gateway. You start with an HTTP front end, which we implemented with the Cowboy HTTP server. It spawns different handler processes that hit our backend. So here, the backend, auth, lease, and receiver are all OTP gen servers that implement their own part of the functionality of the business logic. The backend acts as a multiplexer, forwarding these requests to different subcomponents. We went with Amnesia to persist the session data, and this was very convenient because Amnesia is a database that comes with OTP, so you don't need to install anything else. And also, it has nice support for distributing, for a distributed configuration or replicated configuration. And this could be of interest for us in the future if we want to move to a high availability configuration for the gateway. And then our existing code base is used through these worker processes, which are C++, and they are connected to the Erlang application through the ports driver interface. So basically, there are sub-processes that are, they have a set of pipes connecting to and from the Erlang application. And since they're supposed to be doing the more computationally heavy or more intensive parts, they are usually run one per core. And you have a pool boy worker pool that manages access to them. So since we are C++ developers, mostly this was a new experience for us. And there were some really good parts about using Erlang. So OTP is an excellent value added. It's really difficult to understate. So having these reusable and tested components really allows you to easily build a larger application that is ready. Coming from C++, it's really great to see this focus on tracing and the live inspection of a system. So if you're used to GDB as the state of the art of inspecting the state of a system, opening up Observer where you see the entire process tree in real time is something else entirely. So immutability and functional constructs of the language really help when it comes to the debugging. So there's much less time spent asking who did what, where, why, how. So it's much simpler to understand what's happening. And then the approach to concurrency is really, it makes Erlang feel like a domain-specific language for concurrency. It really makes things simple. You have good tools for automated testing. Dialyzer is a tool that really is actually essential. So Erlang is a dynamically typed language. And Dialyzer allows you to specify type annotations for your functions, and then does the so-called success typing, so checks that things are logically composed together. And this is a very important safety net when you're developing the application. And of course, you can interact with C++ code either by writing functions, implementing functions in C++ that are then linked in, or as I said, with these port drivers where you have sub-processes. And I think for certain cases, you can even implement entire nodes in C++ or other languages, and they will expose the node API, the Erlang node API. And of course, like, not everything is great. There are a few things that could be improved. So dynamic typing is strange if you're coming from C++. Of course, this is a subjective thing, but in my experience, developing things in a dynamically typed language, I feel less confident when it comes to refactor things than if I have a more advanced and more strict compiler. So what this means is that I really have to be thorough, write these type annotations for dialyzer to help me out and to ensure that I'm doing things correctly, and also be disciplined and maintain these annotations as I go forward. Then deciphering Erlang errors can be quite confusing at the beginning. Then you get used to it. But there are things like logger, which can make at least error logging much simpler, and it's very easy to use. Then OTP has a lot of functionality, but it also has quite large APIs. And there are many parameters and switches that are very easy to miss. For instance, certain timeouts that can, then you have various processes dying on you while you're testing and developing, and you don't know what's happening, and it could be to a hidden timeout. So definitely you need a book or a reference if you're new to the language while you're developing. But the overall impression is very positive. So we would definitely use Erlang for new use cases in our architecture as we go forward. And I think one thing we are looking forward to is getting more operational experience, because pretty soon these developments will make it into a release, a public release. Right now they are available, but in the master branch. And then when it's time to deploy these things on a larger scale, more interesting events for sure will happen on the operations part. And I'd just like to mention an associated project. So we actually have a Docker graph driver plugin based on CernVM-FS. So I don't know if you use Docker, you know that the Docker images are composed of multiple image layers, which are superimposed. And when you're doing Docker run, for instance, you have to wait for all the layers to be downloaded until you can actually use the container. And it doesn't matter what you're actually planning to use out of all these layers. They have to be completely downloaded before going forward. And we implemented support for actually storing the contents of these images in CernVM-FS repositories. So what this means is when you do Docker run, this will complete instantly, because all it has to do is mount these repositories, and then the files will be downloaded lazily on demand as they are needed. So we at the Cern, we're using this already in the CI installation, where we are using a lot of Docker images there, and this has really improved the quality of life in this part of the code. So it's also available on GitHub. Give it a try. Also, the CernVM and CernVM-FS projects are turning 10 next year, and we are organizing a CernVM Workshop at the Cern at the end of January. This will be users and developers of CernVM and different other projects, which will be giving talks, and it's open to anyone, so you are warmly invited to join us. I'd like to give a shout out to my team. Jacob Blomer, actually, CernVM-FS arose from his PhD thesis. There's Jared Luganis, our team leader, Petr Hiraut, and Nicola Hardy. Nicola Hardy is actually the technical student who worked on the Docker graph driver plugin. So I thank you for your attention. These are the links on how to get the software and documentation. And if you have questions, I'd be more than happy to answer. Yes, please.
What did you use for implementing the C++ side of the port driver?
POSIX read write. I mean, it's simple. You're not doing multiplexing there.
Yeah, I know. I was looking at it.
Also because you have multiple instances of these workers, and you can do this higher up.
Yeah, I was looking at it the other week for something, and I was thinking, well, how do I turn the Erlang terms into C++ terms? But just hand roll.
Actually, it's read and write, and actually you're using JSON for the messages, and then after the JSON message, if there's a lot of data to transfer, that's a separate binary. Yep.
Can you elaborate a bit on the lease fencing mechanism that you use to protect certain subsets of the file system, and why you did not choose to give each of your gateways a distinct subset of the file system in the first place, so to speak, so that you divide your namespace equally among your gateways?
That's a good point, and we didn't think of it that way. And the leasing, how it's done, is basically if you're asking for a lease on a subpath, it looks if there's a common prefix in the paths, and if there's no conflict, the lease is given, and there's a time to live for each lease. So in effect, it's not very complicated. And if you look at it at the catalogs, which basically have to be rebuilt at the end of each publication, together with this merge operation that happens, they're actually forming some sort of conflict-free replicated data type, because you always have a summation of files of the changes that happens, and this can happen in any order. Also, you don't care. So this reconciliation process is very, very simple. There's not, because we can limit the usage of this. I mean, we say we do not allow release managers to write in the same place, and working under this condition simplifies our work and is enough for the use case that we're looking at.
But you need to have a centralized instance which hands out the release.
Yes.
Do we have any more questions? No? Thank you.
Thank you.